So now we add our fourth hydroxide. What's in solution here? Well, look at this. There aren't any protons in solution. What does it mean to not have any protons in solution? Well, that means you must have a base. I mean, when you see A- in solution, you think that's a weak base. Well, if you see A-2 in solution, that's a weak base too. What kind of equation do you use when you have a weak base? You use a weak base equation. OH- equals KBCB to the 1/2. All I have to do is stick in my value for Kb and my Cb. Well, let's assume Cb is about 1 molar, because we started with a high concentration of solution here. That means I just need Kb. Well, what is Kb up here? Kb, Kb is a value that I get right here from the Ka, because Ka times Kb has to equal to 10 to the minus 14. pKa plus pKb has to equal 14, so the pKb is 4. So I stick that down into here. This is 10 to the minus 4 times 1 square root. That's 10 to the minus 2. My pOH is 2, so my pH is equal to 12. I have now made it through 5 steps. Weak acid case, buffer case, amphiprotic case, second buffer case, weak base case. If this sounds like and feels like a titration, remember it is a titration. And one more step. We can imagine what this step is going to be. I add a 5th hydroxide. This is now a beaker filled with OH-, because the A double minus doesn't matter because it doesn't dissociate much. So my OH- is just equal to my concentration of my strong base. It'll be a pH above 12. Notice that I've gone from a pH that was down around 2 to 4 to 7 to 10 to 12 up to something greater than 12 stepwise. Notice that every calculation I did, I could approximately do in my head. I could certainly estimate it. This shows you the value of making that assumption that a polyprotic acid with the K's far apart is just a bunch of monoprotic acid problems, and the only new thing I need to think about at all is my amphiprotic case.